Hi everybody. In this lecture we'll talk about position and momentum spaces and the uncertainty relations for position and momentum. So let's start about remembering, just remembering a uniform plane wave. A uniform plane wave represented in position and time space corresponds to a complex amplitude here multiplying the exponential to the minus I omega t minus k dot r, which means the phase, the surfaces of constant phase are planes defined through this equation here. So if we remember Planck and de Broglie relations, we can observe that the energy is related to the angular frequency in time, and the momentum of a particle is related to the wave number, the wave vector, and the modulus, of course, the wave number. So we can, applying the quantum mechanical postulates, we can try to find out what are the operators corresponding to energy and momentum. But of course, you must remember that a plane wave is a wave having a definite frequency omega and a definite wave vector. So a plane wave is a function corresponding to a perfectly defined omega and k vector. All right? So if you take the time derivative of that function, plane wave, you'll find minus I omega, and the function repeats. And you can do the same for the gradient of that function. Okay, that's a scalar function. So you'll find out this minus and this minus multiplied, you'll get a plus here. So I, k vector, and repeats the exponential. So this gives you upside. So in terms of an eigenvalue equation, you can say this is the operator here in the spirit of quantum mechanics, all right? This is an eigenvalue and eigenfunction or eigenvector equation where you have an operator, an eigenvalue, and this is the eigenfunction psi of r and t. So the time derivative corresponds to minus I omega here. And here, this is another operator equation in quantum mechanics, which corresponds to the nabla operator. The eigenvalue would be I k vector, and the corresponding wave function, the eigenstate, is a plane wave. So plane waves, uniform plane waves, they are eigenstates, eigenfunctions of ddt, the time derivative, and the nabla operators. All right, this is very important. You can demonstrate these equations easily. So you must remember here that the vector k can be represented, and the angular frequency omega can be represented using Planck and de Broglie relations. So now, if you use a plane wave, the time derivative of plane wave, it's it corresponds to minus I omega, but the energy is just related to the frequency by this equation, or E equals to h bar omega. So you can isolate omega here. It's the energy divided by the h bar in quantum mechanics. So as you can see, you can define an energy operator. The energy operator is an equation which, when applied to a function, produces the eigenvalue of the energy and repeats the function. This is an eigenvalue and eigenvector equation. It's the same thing. So this operator, to obtain just the energy here in the right hand side of the equation, you must multiply this time derivative by the imaginary unit. So minus I squared will give you minus 1, which is plus, just 1. And you must multiply this equation by the h bar. So you eliminate this h bar here. All right, so the energy operator will be given by imaginary unit, h bar, Planck's constant, and time derivative. If you apply this to a plane wave, you will get the energy multiplying the same function. It's the analogous for differential operators of a matrix, an eigenvector, an eigenvalue, an eigenvector, same eigenvector. Okay, this is an eigenvalue equation, right? And for the equation nabla applying to the plane wave, applied to the plane wave, produces the imaginary unit, the k vector, and the same size. So you can replace this using de Broglie by the momentum divided by Planck's constant. This is the wave vector. It multiplies the wave function. And now you know that this is an operator equation corresponding to the nabla operator. The eigenvalues of the nabla operator are I momentum of a particle divided by the Planck constant, and momentum divided by Planck constant is just the wave vector. So if you want to define in the same manner as here for the energy, if you want to define a momentum operator, you need to apply it to the wave function, which is a plane wave, gives you the value of the particular wave function, the particular value of the momentum, the particular chosen k here. You need to specify this operator. So you need to eliminate the imaginary here. So multiply by minus I multiplying I gives you minus I squared. I squared is minus 1, so you get a plus. And you must multiply the equation by h bar. So you eliminate this here. And momentum operator is given by minus I h bar nabla. So this is the important relation we want to show here. So in quantum mechanics, in the spirit of quantum mechanics, I can say the following things. Plane waves, uniform plane waves, of course, they have the form of a function of space-time which is equal to a complex constant. It can depend on the specific omega and k, or energy and momentum p here. For a given energy and momentum, this is a complex number, but it does not depend on space and time. So it does not depend on time and space. and the only space-time dependence goes into the phase, which corresponds to the omega, energy divided by the h bar, multiplying time, minus the momentum p divided by the h bar, which is the k, dot position vector r. This is a plane wave, uniform plane waves, r v eigenfunctions, which means the eigenvectors, eigenfunctions of the energy E operator, the operator of energy, equals to I h bar time derivative, energy operator, and momentum operator, which corresponds to, in quantum mechanics, minus I h bar nabla. So you can see in many textbooks a recipe for first quantizing a theory. They say pick up the classical Hamiltonian, the classical sum of energies of the problem, replace momentum by this operator here. But just it's just a consequence of having the vector k here, the wave number here, and this is related by de Broglie, which is a postulate which was confirmed experimentally, which corresponds to wave number is equal to momentum of the particle divided by h bar. Okay, so a uniform plane wave corresponds to an eigenfunction of a simultaneous eigenfunction of energy and momentum operator. And in this case, the operators commute. So in this case, these operators commute. And it's easy to see that because time derivatives commute with space derivatives. There is no problem in seeing that. So time derivatives commute with space derivatives. So energy operator and momentum operator here, this energy operator in this form here, they commute. So in this case, of course, and so you can find a function, a basis. The bases are plane waves for which you can find simultaneous eigenvalues for both operators, and the eigenvalues for the energy operator is the energy value, and for the momentum operator is the momentum of the particle. All right? It's awkward to say particle here because you're talking about wave. Wave is a field, and the field is the opposite of a particle. But the particle characteristics relates by duality, the proposed relation of the de Broglie principle relates characteristics of waves or fields to particle characteristics by this. You can find a wave vector corresponding to the momentum divided by Planck's constant. And also you can find an angular frequency here which relates to the energy. All right. So this is what do you see when you deal with quantum mechanics. Now that we have found what are position and energy operators, they are just consequences of the Planck and de Broglie principles or relations. You can see the following thing here. If you want a wave, general wave psi of r and t, what not a plane wave, a general wave, all right? What do you want to do? Well, we know that superposition principles apply, so you can integrate over all the omegas and over all the k's in three-dimensional space. Do you have dk of x, dk of y, and dk of z? It's just a volume in k space, and you must normalize here if you want to make it correspond to a Fourier transform. So you can normalize here by a 2 pi. For each Fourier transform, you have a square root of this thing, but you have 1, 2, 3, 4 dimensions. So you have 4 dimensions divided by 2 here. If you have b dimensions, you normalize it according to 2 pi elevated to d divided by 2. So in 4-dimensional space-time, you have a 4 here, but you can also consider one-dimensional problems in space. So this integral here corresponds to just one dk of x. So the dimension here goes to 2, all right? And you can add up plane waves. You know that any field can be expanded in terms of plane waves. It's a mathematical fact. Plane waves do form a complete basis, a complete set of functions which allow you to expand any function in terms of sums of plane waves or integrals of plane waves. So you'll integrate, and that's why I plugged in a omega and k, or energy and momentum dependence, in the constant here. This constant does not depend on space-time, but it can depend on angular frequency and wave vector, all right? And this multiplies the phase factor of a plane wave, which is omega t minus k dot r. So notice it is a Fourier transform. So in quantum mechanics, a function of position and time, a general function, a general wave solution here, must say a wave solution, or any function, as a matter of fact, an arbitrary function is not an eigenfunction of position or of a momentum and energy operators in general. Just a single plane wave is a definite eigenfunction with the exact defined eigenvalue for energy and momentum. So you can normalize it. Okay, you can normalize it properly. 4 divided by 2. The integral of d omega, you can put it here, d divided by the square root of h bar for the energy, and the other square root of h bar you can plug in the inverse Fourier transform, but that's just the normalization. You can do in other fashions. It doesn't matter too much. You integrate of over momentum. Here you will find an h bar square root elevated to the third power, so 3/2 here, and you have plane waves. I put a tilde here. Just remember, these are spectra in energy and momentum, so I can write the psi 0 here. If you put a tilde here, you would eventually drop out this subindex here, and you will have energy and momentum here. It's a function of energy and momentum. This is a function of space-time. To be precise, I would put the momentum first and time and energy in the second place here, because position and momentum are dual variables or reciprocal variables, and time and energy are reciprocal variables, and it multiplies the exponential minus I. I can plug in here energy over the h bar, momentum over the h bar, so the h bar is just a common factor. I can factorize it here. Energy multiplying time minus momentum multiplying position, and that's it. So a general wave of position and time is to be understood as a superposition of states with definite energy and momentum, or plane waves. Plane wave, a single plane wave is a function with definite momentum and energy. But if you add up a lot of plane waves, you'll find out an average momentum, an average of energy, and they are functions of position and time. In quantum mechanics, that's what really happens. In quantum mechanics, I must say the following important consequence, at least uh, for the moment here. Position and time are dual spaces to, or space to momentum and energy. All right. So time is dual to energy, position is dual to momentum. Remember classical mechanics. This is in quantum mechanics. In quantum mechanics, this is what happens. In classical mechanics, position for a particle is a function of time, momentum is a function of time, and they are independent variables. You can plot a phase space here, position, momentum. I will just put single component here, x of t and px of t. It's just a trajectory in phase space, but position and momentum are just functions of time, satisfying, for instance, Newton's laws for non-relativistic particles. So they are the time derivative of the position is equal to momentum divided by mass, if particle has mass, and derivative of momentum with respect to time corresponds to the resulting force. So this is what do you expect for classical particles, classical mechanics. In quantum mechanics, these objects here are no longer functions of time. They are no longer functions of time. They must be converted into operators, all right? So in quantum mechanics, you have position. In quantum mechanics, you'll have a position operator, a momentum operator, all right? And momentum operator corresponds to minus I h bar nabla, partial derivatives, okay? And they are no longer independent in the sense, or maybe bad, bad choice of words, but they are no longer functions of time. They correspond to dual variables in a Fourier domain. So you can have a complete basis in, let us use here just one space dimension, okay? So I will consider x and p of x, all right? They are operators here. Do not confuse it with a unit vector. This is an operator corresponding to the x component of the position vector. And this also is not a unit vector. It's an operator which corresponds to minus I h bar, the derivative with respect to the x coordinate. They are operators in quantum mechanics. And they pertain to dual spaces. All right? This is the position space, and this is momentum space. Corresponds to something in a so-called momentum space. They do not belong to the same basis. They cannot be diagonalized by the same basis. All right? You must have a basis for position, and you must have a basis for momentum in quantum mechanics. Right? If you remember properties of Fourier transforms, you can right now understand why there are uncertainty relations uh, relating position measurements and velocity or momentum measurements. Because if you have a function in one domain with a certain uncertainty, with a certain width in that space, in that, say, the real space, it will have a corresponding uncertainty in the other space. This is a consequence of Fourier transforms. But since Fourier transforms, as we saw previously, can be understood as basis transformations, this is just a consequence in the end of a Hilbert space, distinct basis, and non-commuting operators. That's it. All right, but let us just formalize a little bit more these things. So you can write the space, the, the position basis, right, and the momentum basis, and both will satisfy completeness and orthonormality of a basis for a continuous variable, because you must remember position in the real world is a continuous variable, and momentum also you can introduce just a complete basis here. So this is equal to identity. There are normalization issues here. Some places divided by square root of 2 pi h bar, and here also, or just here you divide by a factor, or just here. But it's just a matter of convention here. I'll put this way, all right? We are talking about just a single space dimension. So I'll have the x here, and the integral is one dimensional here. But if you have a three-dimensional space, you integrate here by the variables x, y, and z, and this is a basis x, y, and z, x, y, and z, or just a vector here. And momentum vector, 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 and it will be converted to a volume integral here and a volume in momentum space, a volume in the momentum space, a volume with units of momentum, right? And also here you have a p prime projected onto another state of momentum. This gives you a Dirac delta, right? This is a complete set. And also you have these vectors, this cat here corresponds to, I will use a redundant notation as Sakurai's book does. So the operator of position operating over its own eigenvector for a particle at a specific position x will give you the eigenvalue, which is the position, and repeat the eigenvector. Here, same thing. Momentum operating over an eigenstate of it corresponds to the eigenvalue and repeat the eigenvector. Notice that this is an operator, this is just a number, all right? This is an operator, this is just a number, all right? That's very important to notice. So let's do the following thing. Well, first of all, we can just represent, as we did before for general Fourier transforms, we can represent this thing for momentum. Say for momentum here, this gives you a Dirac delta. The Dirac delta, if I insert here the resolution of the identity, but express it in the position basis, I will have an integral over dx prime. Okay, I'll put the integral here, but the integral commutes with these vectors here, so I can put the symbol of integration here, and I'll have x. This is integrated over dx, this is the identity. P here. All right, and it must correspond to 1 over 2 pi, the integral from minus infinity to infinity to be a delta over momentum. I must integrate over dx here, exponential I x, put a minus here, perhaps, p prime minus p. If you integrate this over x, you'll get a delta. The sign here, it doesn't matter, just a matter of convention. In fact, the quantum mechanics has a specific convention, so the specific convention is related to, now you can see it's related to this thing here. P, this must correspond to 1 over the square root of 2 pi, the exponential of I p multiplying x dx. If you are dealing with just one component of momentum, let's use this subindex here. Just if you're intending to just generalize, you would integrate over x, y, and z, so you'll have px, py, and pz. For there are other exponentials of this form. This would be another exponential, the y here, and z for more dimensions in space. But you can normalize here for an h bar somewhere, but it's just a matter of convention. So notice that position projected to momentum just gives you 1 over the square root of 2, this thing here, x px, right? I x px. This is this partial part of a plane wave. This just represents a plane wave, all right? So what is a function? represented in position, if you would call it. What is a function of momentum? It's just a plane wave, as we already know from previous analysis, right? So you also would be interested in compute this thing here. Okay, this is the x component of the momentum vector, and this is position, momentum operator, momentum eigenvector, and this is the operator. So this will correspond to p of x operating over one of its eigenvectors. It produces an eigenvalue. Eigenvalue is just a number you can just maneuver to put in front of all the equation, x over p, and we know this is just the exponential I px x. So what would be an operator which applied to this thing here would produce this number here in front of all the things? So this operator here, we already know what it is. It is just I h bar, negative I h bar, the space derivative related to x. Because if you apply this thing to this function here, you'll get exactly this number here, which is the eigenvalue of the momentum operator. So momentum operator corresponds to space derivatives. And this is already known for dual variables in Fourier transforms. All right, for Fourier transforms, right? You have two spaces, say time here and omega there. So if you have a function here, you have a Fourier transformed function there. These are components of the vector or of the ket in the time representation. These are the components of the vector in the angular frequency representation. Perhaps I would represent it as a psi of t. Psi of t is better. Now, so these are the components of this object. Remember, this object is invariant. It's independent of the representation. If you project it to the basis of omega, of the basis of the energy, to say in quantum mechanics, because omega and energy are related by Planck's relation, and time components, the projection of the function over time basis, you have the vector components, which are these objects. You can also calculate the derivatives of the function in time, and this corresponds to minus I omega. So if you want omega here, you need to put the imaginary unit here. So if you multiply it by I, you'll get the I here, the minus I here eliminated. So I, the time derivative of a function of time, corresponds to omega multiplying the function in the dual domain. Also for momentum, you can do the same things. Momentum and position are dual spaces in quantum mechanics. X, X. So if you have a function of position here, you will have a function of momentum in the dual space. All right? And for a space derivative here, the dx of the function c of x will correspond an imaginary unit k of x and repeat the Fourier transformed function. So if you want to eliminate the imaginary from here, you multiply all the equation by minus I, and that's it. Would you use a reversed sign convention? So plus I here, that would be okay, but you would be working with the complex conjugate of the function. The convention is this sign, a plus for time derivatives. The imaginary unit is plus I accompanying the time derivative and minus I accompanying the space derivative. And here, if you want momentum, you multiply here by h bar, and here by h bar. This is the x component of the momentum vector. So it's very, very important thing. In quantum mechanics, position is related to one basis and momentum is related to another basis, and these two bases can be transformed. What is the transformation? Fourier transforms, but they are just basis transformations. So the components of the basis transformations x, p corresponds, this is basis, the coefficients of basis transformations corresponds to e exponential of I x px. That's it. If you are transforming x to px and vice versa, you need, if you want the inverse transform, you need to take the complex conjugate of this number. But that's it, all right? That's it. Momentum and position are not compatible now. Why is that? Because you can calculate, or I must write it here, x and px, or momentum and position, in the given direction are not compatible. Why is that? Because if you consider a function in the real space, an arbitrary function, you can apply the commutator to that equation, to that function. And for a commutator, you have x, x minus the reverse order, right, applied to the function f of x. And you must remember the operator px represented in the position space corresponds to minus a I h bar, the space derivative. So if you do the math here, you will have, first you apply the space derivative here, so you'll have minus I h bar, space derivative of a function of just this position coordinate, and this is also a coordinate function, just function of x, and when you apply the x over the entire function, you'll have a multiplication by x here. And if you do the other operation, you have the following application. It's just I h bar time derivative, and here you must interpret it as x operating over a function of x, which would be just a single function x, suppose, but an arbitrary function. You'll have this thing, and the space derivative operates over a product of two functions. So product, you must derive the first one, the second one, and will be eliminated here. You have minus I h bar x, the derivative of f of x. Well, and and here you'll find I h bar, the derivative of the first, which is just 1, f of x, and you must derive this minus here, cancel out this minus here, plus I h bar x, the space derivative of the function. And this eliminate that. You have just I h bar f of x. So this operator operating on any function of space will produce I h bar the same function. So it is usual to drop out the function from the equation and write the commutator in the following way: x is equal to I h bar. Of course, if you apply an operator x with itself, it gives you 0, because any matrix or any operator commutes with itself, and also p of x commutes with itself, right? And these kinds of commuting relations are called the canonical commutation relations. These are the canonical commutation relations. All right? That is a very important result in quantum mechanics. So, summarizing, remember that x and px operators, or momentum space and position space, belongs to different representations, and they are connected by a Fourier transform. The components of the transformation are just phases, and x projected to p to a given momentum is just proportional. The constant of proportionality doesn't matter so much, but it's proportional to this exponential, which is a plane wave with respect to the position space. Of course, same thing apply to time and the time operator, which corresponds to an energy operator, as a matter of fact. But time and energy commuting relations are just valid for non-relativistic quantum mechanics, perhaps. These are the canonical commutation relations for position and momentum. Now, we can remember the following thing: the uncertainty principle. In general, you have delta, the standard deviation of a measurement of an operator A, which we drop the hat here and let this thing be just delta of A is equal to the square root of the average of the operator squared minus the average of the operator squared, right? This is the average of the squared, and this is the squared average, all right? So this is the variance, and for another operator B, the same thing applies. You must pick up the same state to perform the average, of course. It's related to the same state here. And of course, if you apply these things, you have delta of A multiplied by delta of B is greater than or at least equal to 1/2 the modulus of the average of a commutator. In this case, A and B operators. Okay, this is the uncertainty relation. And if you apply this thing to position and momentum as operators, you'll see they do not commute. So they are operators which cannot be diagonalized simultaneously. So x and p of x is equal to minus or plus I h bar do not commute, or are incompatible. All right? And now it's easy to see that the uncertainty in a position measurement multiplied by the uncertainty, which corresponds to a standard deviation in the measurement. You measure a central value and the standard deviation. You measure an average value and the standard deviation. The products of the standard deviations are greater than or equal to 1/2 the modulus of the commutator with respect to some state specified in the position, and f of x, for instance. But we know that this thing here is I h bar, so the modulus of I is 1, modulus of constant, the numerical constant is the constant, so you have h bar divided by the number 2. So these are the uncertainty principle or the uncertainty relation, which was, I guess, originally derived by Heisenberg when he was trying to study the resolution of a quantum microscope, and he arrived at this conclusion. All right, there are physical intuitions about this equation, but it's just a consequence of representing observables by operators in quantum mechanics. It is a consequence of a given fact, an experimental fact, which are, to be precise, the Planck relation relating energy and angular frequency, and the de Broglie relation relating momentum and wave number, or wave vector if you prefer. And this way you know that uniform plane waves are related to certain differential operators. These operators are related to the momentum here. It's just this proportional to this partial derivative here. So in quantum mechanics, these things do not commute. Position and momentum do not commute. They are equal to I h bar. And for any non-commuting operator or incompatible operators, there are an uncertainty. And the uncertainty in this case corresponds to delta of x multiplied by delta of p of x. It's greater or at least equal to h bar over 2. This puts a fundamental limit in what you can measure with precision. It's a fundamental limit. It's a physical limit. It's not because your apparatus is measuring wrong or anything of that. It's just because the viewpoints in position basis are distinct from the viewpoint or the viewpoints in the momentum basis. They correspond to distinct operators. The basis corresponds to eigenvectors of distinct operators which do not commute. So they cannot be diagonalized by the same basis. The matrices do not commute. It's repetitive, I guess, but in the end, you'll find that the uncertainty in measuring the position will correspond to an uncertainty in measuring momentum. And these uncertainties multiplied must be greater than or equal to h bar over 2. All right. And also, for uniform plane waves, you have zero uncertainty corresponding to momentum. All right. This is zero, because a plane wave has a definite momentum. You have total certainty of the value of the momentum because a plane wave has a specific, exact wave vector. And this corresponds to an exact value of the momentum. So for a plane wave, the uncertainty relative or related to the measurement of momentum is or must be zero. So the uncertainty in measuring the position is infinite, because you have to have a number multiplied by the other must be greater than. So if this goes to zero, this must go to infinity. All right? And it can be understood easily because a plane wave is a field existing over the entire space, and the modulus of that function is a constant. And if you are willing to interpret that function as a probabilistic distribution or a probability density, the modulus squared is a constant means there are equal probabilities of finding a particle everywhere, in any place of the space, in any place. So you can measure the particle in any position. You are not certain where the particle is because you are completely certain what is the momentum. All right? This is a very important consequence of quantum mechanics related to momentum and position spaces. All right? It's a very important thing. There is a joke about the Heisenberg principle, which is related to Heisenberg driving his car at a certain speed. This is faster than the speed limit, and the police officer stops him and asks him, do you know at what speed you were driving, sir?" And Heisenberg said, "No, but I am certain where I am." And the police officer uh, responded to that, "Well, you are driving at a 200 kilometers per hour." And Heisenberg, "Oh, now we are lost," because in the joke, the police officer informed the exact velocity. So Heisenberg, the Heisenberg principle relates a certainty in measuring one thing with the uncertainty of measuring the other. So if you have a certain value for velocity, which means a certain value for momentum, you would no longer know what is the position. So it's a joke related to the Heisenberg principle. But these relations are very, very important, the canonical commutation relations. All right? Well, we can consider a plane wave here. Suppose the plane wave corresponds to space and time, or time and space, if you prefer, but it corresponds to a complex number here, a constant, the exponential of minus I. Suppose an energy is subindex 0 divided by h bar, multiplying time, minus some given momentum p0 dot position divided by h bar. If you perform Fourier transform, I am not interested in the proportionality constants here. So if you want to calculate the components in the momentum and energy space, you will find out that you must integrate over the entire position space. You must integrate over the entire time domain, psi of r and t, and the components, the coefficients of the Fourier transform, they are related this way. I divided by h bar, this is omega, and k vector, energy multiplying time, dot minus here momentum dot position. Okay, it's a three-dimensional integral. If you are interested in just one dimension, this is the x value, and the integrals, just a normalization constant here. I'll put this way here, some normalization constant, which it doesn't matter really. So look at the time integral here. The same applies for each of the x, y, and z integrals. This would give you integral over time, energy minus E0. This is divided by 2 pi delta function. So you'll have a psi 0 here, a 2 pi square root of the normalization you are using, a delta, the direct delta of E minus A0, and three deltas, which is usually represented by delta 3, three-dimensional delta, delta in the x direction, z direction, y direction, or whatever. Momentum is 0. So this corresponds to an impulse, an infinite value for the energy equals to E0, and an impulse for a momentum equals to P0. So in momentum space, you have zero bandwidth for this function. I'll pick up time here. So notice this function, if you pick the modulus squared, this phase goes to unity, and this is the modulus of this amplitude, and you have a function which is uniform in time. So it is a delta in energy. All right, it's a very precise knowledge of the energy value, which corresponds to the frequency omega 0, because energy 0 is equal to h bar multiplying the angular frequency omega 0. So you have perfect knowledge of frequency, but function extends over the entire time domain. Same applies for momentum. If you specify with total precision the momentum, which means you are specifying the wave vector, it's a k0. K0 here is the momentum divided by the h bar, the momentum p0 divided by h bar. You have a perfect knowledge of momentum, but this function, modulus squared, is just a phase modulus squared is unity. So the function is perfectly defined. It has a certain position in a certain value in momentum space, but it's completely uniform in space domain. So if you would plot this thing, for instance, modulus of psi squared here, it's an amplitude distribution over time, you would find a constant, all right? The modulus square is a constant. But, and of course, if you pick up the real part, this is just a phase, but if you pick the real part of psi, you need the imaginary also, you would find something related to a cosinus, just time, but it exists in the entire time domain. And if you go to tilde of omega, which corresponds to energy, or energy here, energy, this axis, you will find a delta here. It goes to infinity here, it's a delta energy minus zero. It's infinite, but it has a width of zero. So completely uncertain in time, totally defined in energy. And vice versa. If you would try to create an impulse in time, a perfectly defined instant in time where a particle was created and then vanishes instantly, instantaneously, you would find that the energy of that particle is no longer possible to determine. And also, if you create a particle in an exact position in space, it's a direct delta in space. But momentum, which means velocity in the end, you don't know nothing about. So, also, if you have this thing, if you have a particle, for instance, created here at a given position, x subindex 0, if you go, this is a psi of x, suppose, if you go to momentum, constant distribution in momentum, right? They are dual spaces, position and momentum. So you have complete certainty where the particle is, but you don't know what the momentum is because the particle can have this value, this modulus squared must be interpreted as a probability density, so it can be here or here or here or any other place in momentum space. All right. Well, that's it. So I'll put an exercise here. Right, it's a very important exercise. And consider the following. Wave function psi of x and time t. Suppose a one dimension is always time plus one dimension space. Okay, so 1 plus 1 dimensions in total. So suppose you have psi 0 here, e to the minus imaginary value E0 divided by the h bar, multiplying time. So the energy is perfectly defined for this function. It's completely defined. You have an energy eigenstate. So it is a Dirac delta in the energy space, right? In the energy variable. But it is a Gaussian x squared divided by 2x0, or say a here squared. So this is a Gaussian in space. Modulus squared here, you'll find a Gaussian. It has a complete determined energy, but it's not localizing in space. And the uncertainty is related to this value of a. It's related to the variance. So this is a Gaussian packet. You can also multiply it by something like this. Multiply it here by imaginary I, some p0 value x divided by the h bar here. So multiply by that. So it's a wave packet moving in the forward direction in the x-axis. It's a wave packet. If you change sign here, move backwards in the x-axis, right? As time passes, this wave packet is a Gaussian. It moves in the x direction here. If you put this p0 to be 0, it's just a wave packet with velocity 0, right? So what we can ask here, all right? Consider this function. First thing, remember that psi of x and time t is just a vector in Hilbert space projected into the base of x and t, for instance. Or say this is a vector rotating in time, all right? And this is projected into the basis of position. So these are components of this vector, right? Consider this. So first thing you need to calculate is the normalization. So this must be equal to 1, and this in space in position components corresponds to the integral over minus infinity to infinity, the modulus squared of the function in space domain, in the position domain, must be equal to unit. So first find the proper normalization, which means find the psi 0. What is this value, right? Because in quantum mechanics, you need to interpret this thing as a physical state which has a norm of unity, because given the state, what is the probability of finding that state? It's 1. So this, apart from a global phase, you could determine from this integral. So you must integrate Gaussian functions, okay? So find the proper normalization. Another important calculations. Find the average of position, the average of position squared, right? These are it will be a confusing statement, but when you integrate Gaussians, x elevated to the n minus x squared divided to a squared dx, for instance, you find perhaps the modulus square here, number 2 will drop out. But if you integrate Gaussians, the n is called the n momentum of a Gaussian. It has nothing to do with momentum here. So, but you can find in the internet or in mathematical books integral tables, values for these integrals, all right? So we can calculate things easily. So find out x squared what are the averages. So what is the average of x elevated to the n? It's the average of a operator elevated to the n with respect to that function. So you can plug in the identity here in the space basis, right? Why in the space? Because you are dealing with the position operator. If you plug in here the resolution of identity, this is the identity matrix with respect to momentum, it will not help you, because when you insert position eigenvalues or eigenvectors here, or the resolution of the identity in terms of its own basis, you can apply directly. So this converts to a number, not an operator anymore. And also you can put the unity here or there. If you have a combined operator, you can calculate the average of x and p, for instance. So you plug in the basis of x here and the basis of momentum here. So you apply momentum there in position to the left. So you must be smart about doing these calculations. And here you have the function. So this corresponds to the integral over dx from minus infinity to infinity. It's the basis over the entire space. This is the value operating to the left on one of its eigenvectors, but this is a Hermitian operator, so the eigenvalues are real. It doesn't matter in this case. You have x of n, it's just the number which is being integrated. And when you project psi over x here, you get the complex conjugate of the function, complex conjugate. And there, if you apply this x to that, you already has the eigenvalues here. You have a psi of x. This gives you a modulus squared of the function. So a x of n average of an operator will be just in position space and integral, right? Probability density here and the operator eigenvalues here, all right? So find this. Find for x elevated to the power of 1, 2, and you can do for n eventually, all right? So find this. Find psi tilde of p and time t, all right? Time you do not need to transform, because if you do the transformation, you will find the Dirac delta. So you don't need to perform Fourier transformation for time. All right. So you need just to perform with proper normalization here. Find out in the Sakurai book. You need to perform psi of x and t here. T you just let it as it is. Exponential of a minus I x px, I guess, divided by the h bar here, integrate over dx, the normalization constant here, you need to find out. All right, you already found the psi zero of the function, and now you have the spectrum in the momentum, or the function in the momentum space. So same thing here, find the average of the operator p, find the average of the operator p squared. For a Gaussian, this is a very interesting result. Calculate delta of x, delta x, and you will see it's greater than or equal to, it's bigger or greater than or equal to h bar over 2, but find out the precise value here, right? You need to find out the precise value of this thing, right? And that's it. It's a very interesting problem. It's related to a Gaussian. As a matter of fact, we are not already calculating the time evolution here, but a Gaussian, when you start with a Gaussian wave packet, it will disperse, all right? So it has a dynamics involved, but for now, just for exercising the math, calculate these things, which I considered here. And that's it for now.